Okay, so our new topic is trust systems, and we are going to see how we are going to analyze the forces in a trust. So what's a trust? Basically, we can say that a trust system is uh, made of members which are straight and flat. For example, you want to design a roof for a sports center. You see that there are steel bars with circular or rectangular cross section, or chassis of a car or a bus. Again, you see that there are frames. They are welded together. In case of a bridge, they are bolt jointed or riveted. And then you form the chassis of the object, of the structure. Now, the point is, this skeleton mainly carries the load in many cases. And the fact is, how can we design such a system, such a skeleton? What are the forces? Because we need to know the load-bearing capability of the structure. Now, here, as you see, we have a representative of truss system. So it is fixed at point A, pin jointed hinge here, and there exists a roller at point C. Now we have a force at point B, an external force here, and certainly we have the members AB and AC and CB. We have three members, three truss elements of our which belongs to our design. Now, there are two methods that we use mainly for analyzing the forces in a truss system. And the first method is method of joints. Now, what is method of joints? As you see, the truss elements are joining together, where, for example, at point B, this is one joint. Now, certainly what we do is we write the force equilibrium in a joint. Now, if we isolate each member and assuming that regardless of the joint type of joint at point B, it can be welded, it can be bolt jointed, it can be riveted, or whatever it is, doesn't matter. We assume that it is pinned at point B in method of joints. Now, this basically means that since we don't have any load all along the member, for example, BC or AB, it carries load only along its direction. And certainly this means that there is either tension, which tries to elongate the structure, or compression, which tries to shorten the structure. And in fact, we write the force equilibrium on the pin in this case. So we draw the free body diagram. This is the first step. Now, when we draw the free body diagram on the pin, free body diagram of the pin at point B, we see that we don't know the forces. Okay, so we don't know the magnitude of the forces, but certainly we know the direction because they are in the direction of they are always in the direction of the truss member. So, for example, the force in the AB is in the direction of AB, or force in the AC is in the direction of the AC. It is identical in the member BC, so it is in the direction of the BC. We know the direction, but the point is we don't know the magnitude. And in fact, Therefore, we can write the force equilibrium, and we know the directions. We can give the directions of the forces at point B. Now, there is one thing that we have to be careful, since we don't know whether they are tension or compression, and in fact we don't know their magnitude. We assume that all the forces are tension initially. In general, this is general. Of course, after the calculation, if the force is compression, we will find its magnitude as negative. Now the point is, how do we show the tension? Now, as you see, this is the force. For example, FBA is the force acting on the pin B. Now, certainly, the force, if the force on P is in this direction, like this, the force on the truss has to be in the opposite direction, but has the same magnitude. Now, this is one thing. Of course, you can take the force compressive, but this is not generally preferred. This may cause some confusion. Then the force has to be directed to the pin. This means that the force on the truss element is in opposite direction. So this is how we draw the free body diagram of the joint at point B. Now, what is the next step? Then the force equilibrium. Because at each joint, sum of the forces has to be equal to 0. Sum of the forces in x direction has to be equal to 0, and sum of the forces in y direction has to be equal to 0, since the joint B acts like a particle. So this is what the method of joints. Initially, how we solve the problem? Of course, what we do is, in this case, we first begin by finding the support reactions. Since the overall structure is in static equilibrium, so the first step is finding the support reactions. Via force and moment equilibrium. Then second step is finding the forces acting on the truss members by using force equilibrium at each joint. So these are the two main steps. In fact, in method of joints, it will be much more clear when we begin to solve some examples. Now, this is what the method of joints is. Now, we have another method of sections. Now, the point here is we have members. Okay, so truss members. And What happens is this: when there is a tensile force, okay, so which try to elongate the structure, certainly wherever we cut the structure, there will be some internal forces. So this force is basically transmitted through the structure. And if we cut it at a point, this basically means that there is an internal force which is transmitted through. And regardless of the location that we cut the structure, okay, each piece, each part has to be in static equilibrium again. So basically, this means that this part is in static equilibrium, has to be in static equilibrium, and the other part has to be in static equilibrium as well. It is the same if the forces are compressive. So the force can be compressive. We can cut it at an arbitrary point. And again, you have to keep in mind that each piece has to be in static equilibrium. So what it means? This basically means that internal forces are tension if the element is, the member is under tension, and internal forces are compressive if the member is under compression externally. So this is what it means. Now let's see how it works, how we can use these ideas. Now just consider we have a very complicated truss system. Generally, we have many numbers of members, elements, truss elements. And in fact, we need to know sometimes the forces acting on particular members. We know that the structure is in static equilibrium. So again, the first step is finding the support reactions always. So we find the support reaction at point E, and we find the support reaction at point D, for example, for this problem. But indeed, maybe we are asked to find the forces coming to the member BC, member GC, and member GF. Instead of solving the whole system, what we do is very simple. We cut the structure from a proper location. Then we write the internal forces. So when we cut it, of course, we can say that there are internal forces. We can choose either side of the part. So again, we generally prefer tensile forces. For example, here FBC. Okay, FBC is tensile, FGC is tensile. It is shown that FGF is compressive, but of course, this is better. It's better to take the FGF as tensile as well. Okay, but on the other half of the structure, certainly the force must have the same magnitude but opposite direction. As you see, FBC here is in the opposite direction, and FGC is same, and FGF is the same. Now the point is this: you can choose either side in order to find the forces coming to the members GF, GC, and BC. So these are the forces, magnitudes of the forces to be found, which is asked to us, for example. Now, in this case, the proper choice is the most easiest part. Now, if we choose the right-hand side for the solution of the problem, for example, we have to find the support reactions, Ty, Tx, and Ex. First, from the static equilibrium of the structure, global structure. But if I choose to solve the right-hand side, solve the problem through right-hand side, I don't need to calculate the support reactions. Now, I have three unknowns, and in fact, this means that I need three equations. Of course, each part has to be in static equilibrium. Now, I know what the static equilibrium conditions are for plane problem. In fact, for a plane problem, sum of the forces in each direction has to be equal to 0, and moment with respect to any point has to be equal to 0. Now, this basically means that I will write the static equilibrium. So I know the external forces. So the forces are transmitted through these joints to this cutted surface. And as a result, this piece has to be in static equilibrium. I have three equations and three unknowns. If you cut the structure in an improper way, so for example, you may need to, or you want to cut the structure in a different way, and you want to find the forces in members BC, GC, CF, and CD. Okay, you see that you have now 4 members, and if you want to use this, use the idea of the method of sections, now it will not work here, because now certainly when you cut the structure like this, of course you cannot take the joint C, because now joint C is isolated. And if you write the static equilibrium for the rest of the structure, you have 4 unknowns and 3 equations. This basically means that you cannot solve it. In fact, your cut surface or cutting line should cross 3 members at each time. This is the most proper choice. So the better is to first cut like this and find these 3 members. And if you find this one, certainly you can write the static equilibrium for joint C, and you can find the forces in these 2 members as a next step. So it will be much more clear, I guess, when we begin to solve some examples.